Bismillah ar-Rahman ar-Rahim. This is Muhammad Abdul Ghani, and this is the second part of our review of the course on ABC of biomedical research for cardiologists. Today we will cover a couple of important topics, including basic statistical terms, risk and odds, choice of statistical tests, especially diagnostic test studies. Let's start with basic statistical terms. The premise of biomedical research is to take a sample from a population of interest, and the findings we get from this sample are meant to be extrapolated to the population from which we have taken our sample. During this process, we may face some types of error. The first group is systematic errors, or so-called bias, which could be a selection bias, performance bias, detection bias, and etc. Bias typically leads to error in a fixed direction and can be minimized by proper design and execution of a study. Another type of errors are random error, type 1 and type 2. These can be minimized by taking a larger sample, but we have to accept that these are inherent to any biomedical research, and we have to set the margin of error that we consider acceptable. The p-value, or the probability value, indicates the likelihood of the type 1 error, or so-called false positive result. In other words, it is a measure of the likelihood that our results are not true, they are only by chance. A margin of error of less than 5% is widely accepted in biomedical research, and therefore a p-value of less than 0.05 is typically considered to indicate statistical significance, or in other words, is accepted as indicating that our results are unlikely to have occurred by chance. Type 2 error is the likelihood that our negative results are false. It's false negative. And in biomedical research, we typically accept a margin of error of 20%. And in the other term that is closely related, but actually is the other face of the coin, is the statistical power. And it's broadly accepted that a study shall have a statistical power of at least 80%, which indicates that we have 80% that our negative results are true and not false negative. When we interpret the p-value, we have to see that the p-value is a metric that our results are real and not due to chance. It's not a metric of the magnitude of a difference or the strength of a relationship. Another point is that statistical significance doesn't always indicate clinical significance. Finally, if our results are not statistically different, this doesn't necessarily mean that our groups are the same, because an underpowered study with relatively small sample size is likely to yield a false negative result. And even when the study is adequately powered, most study design would accept a 20% margin of type 2 error, or false negative results error. So what determines an adequate sample size? The margin of type 1 error that we accept, the margin of type 2 error that we accept, or in other words, statistical power, the smallest effect size of clinical interest, or in other words, the expected or hypothesized in-between group difference. Finally, the expected variability of the outcome, or the expected frequency of the incidence or prevalence of the outcome of interest, especially in the control group. So, if we aim at a lower margin of error and we expect a relatively small difference between the groups of interest, if we expect a low incidence or low frequency of the endpoint of interest and a large variability of that outcome, then the sample size has to grow bigger. Let's move to the types of variables. Variables can be qualitative, quantitative, or time to event data. Qualitative or categorical data can be ordinal following a certain order, nominal with no such order, or binary when there is only two categories or two possibilities. Quantitative or numerical data can be discrete or countable and could be continuous, taking any value within a range. Time to event data is a type of data where there is an event indicator, which is typically a yes/no variable, combined with a time variable, which is typically a numerical variable. Both quantitative and qualitative data can be summarized and should be summarized during our research. Qualitative data can be summarized as frequencies and proportions, or numbers and percentages. Quantitative data can, on the other hand, be summarized into three groups of summary statistics: indices of central tendency, indices of variability, and description of the distribution or symmetry of the data. Central tendency parameters include mean, median, and mode. Measures of variability could be range, interquartile range, variance, or standard deviation. Let's talk about confidence interval. A 95% confidence interval is a range of values around the sample mean, which contains the population mean. A 95% confidence interval represents the uncertainty of the sample in estimating the population mean due to sampling error. A wider confidence interval indicates greater uncertainty that the sample represents the population and vice versa. A larger sample from the same population would yield a narrower confidence interval and indicate a greater certainty. Suppose we have a population of interest from which we have taken a sample. We calculated the sample mean and we expect the population mean not to be identical to that sample mean. We expect some extent of deviation between the sample mean and the population mean. And the 95% confidence interval around the sample mean gives us a 95% confidence that the population mean is within this range. If there is excessive variability in the sample, then the confidence interval will become wider and the certainty will be less. If we take a bigger sample, it will be more representative of the population, the certainty will increase, and the confidence interval will get narrower. The confidence interval is related to the standard deviation and to the sample size. Suppose we have a mean of a range of readings or a range of observations. The confidence interval will extend on either side of the mean, spanning over a margin of error. So the confidence interval equals the mean plus minus margin of error. Suppose we are calculating a 95% margin of error. In this case, we will multiply the number of 1.96 by the standard deviation divided by the square root of the sample size. Let's move to another important concept, the concept of risk and the concept of odds. Suppose we have two groups, a treatment group and a control group, each consisting of 100 patients. Suppose that the outcome of interest occurred in 2 patients in the study group and in 3 patients of the control group. This translates to an absolute risk of 2% and 3% respectively. Doing the simple math, the absolute risk reduction is 1%. However, the relative risk in the study as compared with the control group is actually 2/3. So we have a risk of 2 a risk of 3, so the relative risk is actually 67%. And in other words, the relative risk reduction is actually 33%. Let's take this sample and this example. Suppose we have a study group of 100 patients and the control group of 100 patients, out of which 10 patients in the first group had an event of interest and 40 in the control group had such an event. So the absolute risk in the first group is 10% and in the control group is 40%. Again, absolute risk reduction is 40 minus 10 is 30% or 0.3. From this number, we can calculate the number needed to treat, which is 1 divided by the absolute risk reduction. In this case, it will be around 3. So, in other words, you need to treat 3 patients with the treatment of interest to prevent 1 event. Relative risk is the product of 10 divided by 40, which is 25%, and we can say that the relative risk reduction is accordingly 75% or 0.75. Odds ratio is a different concept, and in this example, it's around 17% or 0.17. Let's see how it's calculated. First, we have to make this distinction between risk and odds. Risk is just the probability of an event happening. And odds, on the other hand, is the risk of an event happening divided by the risk of it not happening. So if we have 2 groups, 1 and 2, and the outcome either happens or not happening, the risk will be the product of dividing the number of patients with the outcome divided by the total number of patients in the group of interest. Odds, on the other hand, is the product of the division of the number of patients with divided by the number of patients without the outcome of interest. Relative risk, odds ratio, and the related concept of hazard ratio is all of these are represented in the same way. If they are more than 1 and the confidence interval of them doesn't include 1, this indicates that events are significantly more likely in the treatment group compared with the control group. If the value is less than 1 and the confidence interval doesn't include 1, this indicates that events are significantly less likely in the exposed than the control group. Therefore, if the confidence interval includes 1 or straddles 1, then it is uncertain whether events are more likely in the treatment or the control group, which indicates that the difference in risk or odds is not statistically significant. Let's quickly take a look at the process of choosing a statistical test. In the process of choosing the right statistical test, we have to ask ourselves a couple of questions. The first and most important is, what is the purpose of the analysis? The second question is, what is the type of variables? And finally, how many groups and are they related or not? The purpose of our analysis could be to compare some groups, either 2 or more. It could be to explore the relationship between 2 factors. It could be a time to event or survival analysis, and it could be a diagnostic test study. If we are comparing groups, we have to make a distinction between 2 types of comparisons according to the type of the variable. So if we are comparing continuous data or numerical data, then we will have to use the appropriate tests. And these tests are different from the situation when we are comparing some qualitative data. The other factor that will determine the type of the test is the number of groups, the distribution of the variable, normal versus not normally distributed, and whether the groups are paired or not. The test of a relationship between two factors usually is conducted using correlation or regression. Time to event analysis is typically done using the actuarial analysis or the Kaplan-Meier method. Actual analysis is another alternative, and the relationship between an independent variable and a time to event data is usually done using the Cox regression analysis. In diagnostic test studies, we are concerned with proving that there is a good agreement between our method and the standard, and to measure the extent of disagreement between these two methods, or the so-called bias. Sometimes we need to figure out a cutoff value, and this is typically done using ROC curve analysis. And finally, we often want to calculate the diagnostic performance indices or the diagnostic accuracy indices. Let's start with an example of two versus more than two groups compared regarding a couple of variables. Suppose we are comparing numerical variable in two groups. In this case, we will use the student t-test if our data are normally distributed. If they are not normally distributed, then we will use the Mann-Whitney U-test. If we are comparing more than two groups, our default test is ANOVA. In case data are not normally distributed, then we will use Kruskal-Wallis test. If we are comparing two or more groups regarding a categorical variable, then chi-square test is the most commonly used. The most commonly used test to compare time to event data using the Kaplan-Meier method is the log-rank test. If we are exploring the relationship between two variables, the choice of the test depends on the nature of the outcome or the dependent variable. In most cases, we will use some kind of correlation or some sort of regression. This is a flowchart that can help you find the appropriate test for your analysis. Again, it depends on the purpose of your analysis, whether it's to highlight a difference or to explore a relationship, the type of the variable you're comparing, continuous versus categorical, and the number of groups, and whether these groups are related or not related. Let's focus on a certain type of studies that we frequently face in our readings and in our research practice, the diagnostic test studies. In these studies, you are introducing a new modality of diagnosis or a new method of diagnosis, and you want to prove that it's accurate. Actually, it's not only accuracy that matters. We shall always try to prove that our new method is also precise or reproducible. To prove that our new method is accurate, we need to prove that it agrees with a standard method. And this agreement can be documented using so-called kappa statistic if the variable is a qualitative variable. If it's a quantitative variable, then we can use intraclass correlation coefficient. And the bias between our method and the standard method can be highlighted using the Blend-Altman plot. To identify cutoff value, ROC curve analysis is most commonly used. And for any test that yields a yes or no or a binary outcome, we can always calculate the diagnostic performance indices. These include sensitivity, specificity, positive and negative predictive value, and diagnostic accuracy. Thank you very much for your attention.